Hi. So today we're going to continue our discussion of the Hamming code, which is one of the first error correcting codes that one should learn. Okay, so let me just recall some stuff. So recall that a code is just any subset of z2 to the n. So maybe I could say a code of length n. And a linear code is a subspace of z2 to the n. And the nice thing about linear codes is they have this extra structure, right? And why is z2 to the n kind of important? So there's a couple of reasons. So why is z2 to the n? Right, so first of all, you can convert messages into binary strings quite easily by some scheme that you want. And so any message that you want to transmit, you can break it up into bit strings of length n and view it as a vector in z2 to the n. Right, so we go from our message that we want to send to somehow encoding it as a binary string or a binary word, and then we can view it as a vector in z2 to the n. So it's a very natural vector space in which to act, in which to live, because binary strings are very natural things. All right. That's really the main reason. Another thing is that we can picture it. Right? So, in computer science or whatever, you learn about binary strings of length n, but rarely do you draw some sort of geometric picture. But once you can think of it as a vector space, you can picture it. You picture it as always, I'll draw the picture in dimension 3. You picture it as the vertices of the unit hypercube. Right, so this picture here. So, for example, in dimension 3, there are 8 vertices. In dimension 4, there are 16. But you can picture them as vertices in the unit hypercube. And then every time you flip a bit in your message, you move along one of the edges of the cube. Right? So, like in z2 cubed, this vertex is 1, 1, 1. And it's connected to 3 vertices. And it depends upon what you choose as your x, y, z axis. But I think what I did last time was I called this one 1, 1, 0. I called this one probably 0, 1, 1. And I called this one 1, 0, 1. So you can see that because there are 3 edges leaving every vertex, because there are 3 possible bit flips to take you to the other vertices. And then the third reason that it's nice is that we can do linear algebra. And because we can do linear algebra, if we have a linear code, we know a lot of things about subspaces, and so we can bring all of that knowledge to bear on a linear code. But a code is just a subset of z to the n. Okay, and then we introduced the notion of distance. So there's a notion of distance between any two vectors in z to the n, called the Hamming distance, where the distance between two vectors is just the number of bits where they differ. Right, so from this vector to these vectors, all these green vectors are distance 1 from the blue vector. But the green vectors are distance 2 from each other, right? Because they differ from each other in 2 places each. And you can visualize this as, because we have this unit cube, it's the shortest walk along the edges of the unit cube from one point to another. That's the distance. Okay, and then we said if you have a code, the distance of the code is just the closest any 2 points in the code get to one another. Okay? So let me just scroll down a little bit. 5, if C is a code, then the distance of C is the minimum of the distances between U and V, where U and V are in C. Okay, and why will this be important? Let me just move this up so we're sort of all still on one slide. This is going to be important because if we are assuming that over the channel that we're sending our message, you have a small chance of error, well, if the vectors in our code are far apart, if we make just one error, then we'll be able to tell which actual vector was sent. Right? The idea is let your possible messages give you a code, a subset of z to the n, where the points are far apart from one another. Right? So I'm only going to take some of the vectors in z to the n, but I'll choose them to be far apart from one another. And if they're far enough away from one another, then if there's an error in the message when it's transmitting, so it goes from one vector to another, but I'll know which vector it came from because my vectors are far apart, so it has to come from sort of the closest one. That's the idea behind an error correcting code. Okay, the idea behind an error correcting code is essentially all on this one slide, except for what I just said, which is you pick a set of vectors in z2 to the n that are far apart from one another. That's the whole trick. And you let those be your allowable messages, and then you can know which message you got sent, even if there's an error. That's why it makes sense to call any subset of z to the n a code, because you could do this with any subset. Just make sure that you pick vectors that are far apart from one another. Again, the point of choosing linear codes is because then you have the power of linear algebra to help you. Okay, so now I'm going to introduce a new definition that it didn't introduce last time. Definition. Sorry, I'm having tablet issues. A code C in z2 to the n, we say that it corrects t errors if for every vector u in z2 to the n, there is at most one vector in C that's within distance t of u. Okay, and again, the idea is, let's say we want our code to correct one error. Well, that means that if there's one error, that's like you sent a vector and one of the bits got flipped. So it ended up distance 1 away from where it needed to be. But if there's at most one vector that's distance 1 away from that vector that you receive, then you know exactly which vector in the code it was. Right? So this generalizes to t. If you want to correct t errors, well, introducing t errors means you make t bit flips. Right? Introducing t bit flips means that you walked a distance of t along the edges of the unit cube. So if there's there's only one vector that's within t of u, the message that you receive, then you know exactly which vector it came from. You actually know exactly which vector was actually sent to you. So that's why we use this terminology for correcting t errors. Again, this just means basically that every single vector in z2 to the n, there's only one vector within t units of it. Now, what does that mean about the vectors in C? Because if you think about it, let's say you want to correct one error. So if you want to correct one error, t equals one error, then what we want is a subset, a code here, such that every vector in z2 to the n is distance 1 from at most one vector in C. Well, what does that mean about the vectors that are in your code? They need to be more than one apart for sure. They also need to be more than two apart, right? If I had two vectors that were distance 2 apart, right? So again, if I'm drawing this unit cube like this, these two vectors are distance 2 apart, right? But these can never correct one error, because if you received this vector, you wouldn't be sure where it came from. So certainly you can never have a code that corrects one error where any of the vectors in your code were distance 2 apart. But if all the vectors in your code are distance 3 apart, then that means that if you get a vector, it can never be within one of two vectors at the same time, right? Because then they would be distance 2 away, actually. So we need the vectors in C to be at least distance 3 from one another. Okay, and we should prove this. It's basically, we basically understand the proof, I think, but oops. So here's the theorem, and then I'll state a more general theorem later. A code C corrects one error if and only if the minimum distance between any two vectors in C is greater than or equal to 3. Okay, so the proof is, we essentially just gave it. So suppose, so I guess this is the backwards direction. So I'll prove the converse instead. So suppose that the distance of C was not greater than or equal to 3, i.e. was less than or equal to 2. Well, by definition, this means that there are two vectors that are within 2 of one another. By the definition of distance, there exist two vectors u, v, and c, such that the distance between u and v is less than or equal to 2. Right? Then either u and v have distance 1 away, or u and v are distance 2 away. Right? I guess I should have said this notion of distance is over all u and v in C that are not equal, of course. Right? Okay. Well, if the distance from u to v is equal to 1, then the distance from u to u is equal to 0, and the distance from u to v is equal to 1. So by definition, C can't correct one error because there are two vectors that are within distance 1 of u. So there exist two vectors in C such that they are distance less than or equal to 1 to u. Right? So u itself and v. So C does not correct one error. Because the definition of correcting one error means that every single vector is distance at least, for every single vector, there's at most one vector that's within distance 1 of that vector in C. Right? If the distance is 2, then u and v differ in 2 bits. So what you do is you just flip one of those 2 different bits, and then you have a vector that differs from u in 1 bit and differs from v in 1 bit, right? In other words, that means that along the unit cube, u and v are 2 steps away from each other, which means that there's a vertex in the middle. Right? So then there exists a w, which isn't in our code necessarily, right? But it is in z to the n, such that d of uw equals 1 and d of vw equals 1. And again, by definition, C cannot correct one error. So we does not correct one error. So we've proven that the converse of we've proven this direction by contrapositive. Sorry, I'm totally wrong. We've proven this direction by contrapositive. We proved if not Q, then not P, which proves if P, then Q. Sorry. Okay, so conversely, which means I need to prove that if D of C is greater than or equal to 3, then C is one error correcting. To correct one's error, when C corrects one error, we can prove that by the contrapositive 2. So suppose C is not one correcting. Right? That means that there exists a vector w in z2 to the n, which is distance less than or equal to 1 from two vectors in C. And there exists u and v in C, such that the distance from u to w is less than or equal to 1, and the distance from v to w is less than or equal to 1. But the point is now I can get from u to w in one step, and from w to v in one step, which means that I can get from u to v in at most 2 steps, right? So there's some chance here that w is either u or v, but then the distance from u to v is less than or equal to 2, because I know I can get from u to w in at most 1 step, and from w to v in at most 1 step. And that is exactly the negation of so d of c is less than or equal to 2. Sorry, I'm having tablet issues. You can't see, but a thing keeps on popping up. Whoa. I lost so much stuff here. Oh my gosh. Okay, sorry. So d from u to v is less than or equal to 2. So d of c is less than or equal to 2. So d of c is not greater than or equal to 3, which proves that direction by contrapositive. Okay. So the whole idea, well, one of the main ideas behind coding theory is to pick out subsets of this vector space that have this property that the messages are far apart. Now, how far apart do you need to be to correct t errors? It's basically the same argument. To correct one error, you need to be 3 apart, because that way, if you walked 1 in any direction and 1 in the direction, you wouldn't meet in the middle somewhere. So if you want to correct t errors, you need to have distance 2t plus 1. Because that way, if you walk t in one direction and t in the other direction, you never overlap. Okay, so the general theorem is that C corrects t errors if and only if the distance of C is greater than or equal to 2t plus 1. Again, this means that your vectors in your code are spaced far apart on the unit cube. And then, of course, what you want is you would like to pick as many vectors as you can in your code such that they're still far enough apart to correct errors, right? And the Hamming code is one efficient way to do this if you are wanting to send messages of length 4, right? Then you encode it as a vector of length 7, we talked about last time. We didn't prove that it corrected one error, but it does. In fact, we're going to introduce now a generalization that includes what we talked about last time. Okay, so here's the definition. Fix a positive integer L then the generalized Hamming code for L, right? So this depends on L, is the linear code in Z2 to the N, where N is 2 to the L minus 1. With parity matrix P, whose columns are all the non-zero elements of Z2 to the L. Okay, so what we're doing is we're fixing a positive integer L. So in our previous case, L was 3, right? That was the original Hamming code. Right, so in our example, L was 3, which meant that N was 2 cubed minus 1, so it was 7. And what we're doing is we're taking the matrix whose columns live in Z2 cubed and whose rows live in Z2 to the 7, right? Point is that there are 2 to the 2 cubed minus 1 non-zero vectors in Z2 to the L. And maybe I should just point back to our example from last time. You still have this on a slide somewhere. It was this thing, right? No, it was the next one. This parity matrix thing exactly gave us all of the non-zero vectors in Z3, and there were 7 of them. And then we just defined the code to be the null space of the matrix, which made it a subspace. Okay? So the point is that this now works for any L, not just L equals 3. So then the null space of P is a linear code. And that's going to be the generalized Hamming code. Okay. Now, a code just gives you a set of messages that are allowable to receive. That way, when you receive a message, if it's different from an allowable one, you know what the allowable one was because there's only one allowable message that actually came through. And the Hamming code is one way to get a nice set of allowable messages. Of course, you still need the scheme to take a message and turn it into an allowable message, right? Like what we were discussing with the original Hamming code is you take a message of length 4 and you append some digits, and now all those things end up being vectors inside of the Hamming code. And we'll discuss a nice way to do this after we prove that the generalized Hamming code works, right? That the generalized Hamming code is a one error correcting code for any L. Okay, so here's the theorem. The generalized Hamming code C has d of C equals 3 and is therefore one error correcting. Okay, and it's a pretty nice big subspace of Z2 to the N, right? Which means that you have a lot of, you're being pretty efficient with the number of bits you're sending. You're getting a lot of allowable messages in a few bits. Okay, so here's the proof. So note that for any code, you can think of this number, the minimum distance between any two elements in C, is the same thing as the minimum distance from any vector to 0. Okay, remember that this distance d of c is defined to be the distance between the minimum distance between any two vectors in your code. But what we're saying is actually it's enough to just look at all of the distances to 0. And that's because it's a linear code. So linear here is actually very important. So suppose that you have two vectors in your code. Then with distance d of uv, the point is that because you're a linear code, you can do a trick. A linear code is a subspace, right? Which means that it's closed under addition and scale multiplication, right? So then, since C is a subspace, U plus U, which is equal to 0, and U plus V are both in C. Right? I guess we already know that we already knew that 0 was in C, but you can think of it as U plus U or as U minus U. Doesn't matter. And the point is that if you add the same vector to any two vectors in your subspace, the distance is the same. Right? It's just like you're translating the picture, right? The picture is that U is here and V is here. But then if you just translate the vectors so that U is at the 0 spot, right? So U is here, V is here. If you translate them by subtracting U or adding U, that's actually the same thing. So maybe it makes more sense to say subtracting to think. But remember, in Z2, +1 is the same thing as -1. If you translate the vectors by subtracting off U, the distance between them is still going to be the same. These two green lines will still have the same distance. Right? So distance is preserved when subtracting a common vector. So the distance from U to V is the same thing as the distance from 0 to U minus V. And U minus V isn't C. So in other words, every distance between two vectors in your code is achievable by a distance from 0 to a vector because it's a subspace. It's closed under addition and scale multiplication. Which means that we don't just need to look at every pairwise distance. We just need to look at every vector's distance from 0. Okay, so now we just need to show that the generalized Hamming code we talked about, every vector is distance at least 3 from 0. In other words, every vector has at least 3 ones in it. Right? The distance from 0 is the same thing as the number of ones in the binary string. Okay, so we just need to show that for every W in C, the distance from 0 to W is at least 3. Which is if and only if W contains at least 3 ones. Like 1 bits is the way I'll say it. But now we can think of the parity matrix, because remember, the definition of this code was the null space of P. So recall that C is the null space of P, the parity matrix. Well, we can show that no vector with at most 2 non-zero bits is in the null space of C. Sorry, the null space of P. Okay, well, if W has 1 non-zero bit, and P of W, P times W equals 0, rather. Well, what does this mean? That means that W is like a standard basis vector, which means that P times W is just picking out a column of P, which means that one of the columns of P is 0. But that's impossible because we said that the columns of P are the non-zero vectors in Z2 to the L. So this implies that a column of P is the 0 vector, which is false by construction. That we defined P to have all non-zero columns. Okay, but if W has 2 non-zero bits, and P of W is equal to 0, now what this means is that when you multiply P by W, what you're really doing is you're adding 2 columns of P to one another, right? Because this is exactly P times one standard basis vector plus P times another standard basis vector, right? So W then would be like EI plus EJ. So P times W is PEI plus PEJ, which is like PI plus PJ, 2 columns of P. But if 2 columns sum to 0 in Z2 to the N, then they're the same column, because addition is the same thing as subtraction. But this is also false by construction. We constructed P to be the matrix whose columns consisted of every non-zero vector in Z2 to the L exactly once. Okay? So because of the way we constructed our matrix P, it cannot have any vectors with 1 non-zero bit in the null space, and also can't have any vectors with 2 non-zero bits in the null space, which means that every vector has at least 3 non-zero bits, which means that the distance of this linear code is at least 3. It's actually exactly equal to 3. Okay, so this is really cool. This is just basically just a really simple linear algebra argument that shows that the Hamming code corrects one error, because we could understand everything in terms of linear algebra. Now for the part which is how you actually use the code. In general, how do you use this code to transmit messages? So we already saw how to do it for when L equals 3, right? You can take all possible 4-bit strings. You can append these 3 bits that put them inside of the Hamming code. Then when you send that code over, you're now sending a vector with 7 bits in it. There's at most one, and if there's at most one flip, then you can uniquely identify which vector it came from, and then you can figure out what the original 4-bit string was. Okay, so how to encode and decode using the Hamming code. Okay, so let's suppose that we have, so let C be the generalized Hamming code. For some fixed L. And let's let G be the generator matrix. So remember, the generator matrix was just a matrix whose rows gave you a basis of the Hamming code. And the Hamming code, again, is a subspace. It's a linear code. So the parity check matrix, remember, we call it the parity check matrix. Had size L by 2 to the L minus 1, right? Which means that the null space of P has dimension 2 to the L minus 1 minus L, right? by the rank nullity theorem. So let's call this right. So the generated matrix, therefore, is the dimensions of G is 2 to the L minus 1 minus L by L. Right, because that's the dimension of the null space of P by L. So let's call this thing K. Okay, so in our original Hamming code example, L was 3, 2 to the L minus 1 was 7, and K was 4. And 4 was the length of the messages that we were able to encode using the Hamming code, so that's why I'm calling it K. Okay, so now, given a word that I want to encode, V in Z2 to the K, encode it as W equals V transpose G. Okay, so remember now that V transpose is a 1 by K vector, and G is a K by, oh, sorry, this is wrong. This should be 2 to the L minus 1. 2 to the L minus 1, and so your result is a vector that's 1, sorry, V is 1 by K, which means that V transpose is 1 by K, which means that V is K by 1, of course. But V transpose G will be 1 by 2 to the L minus 1. I guess I should do it like this. Which means that we're taking vectors that are length K, and we're coding them as vectors 2 to the L minus 1. Which is exactly what happened with the Hamming code. We took vectors of length 4, and we encoded them as vectors of length 7. And the point is that what this vector does is it takes some linear combination of the rows of G, so it's definitely inside of C. So this is how we get from our message that we want to send to encoding it in the Hamming code. Okay, and one thing that you'll show in the homework is that you can always choose the generator matrix. So I guess I'll just write on problem set. You'll show that you can always write the generator matrix as the identity matrix and some other stuff on the side. And so when you encode your message, the first K entries of W will be equal to will be equal to V. So like the nice thing is that when you send your encoded message, like the plain text is still sitting out there as the first K entries of your vector. Right, so this will show that W will look like V and then some stuff. V transpose, I mean, as a row vector. But remember, the row vector, column vector doesn't really matter. It's just to make the sizes match up. Okay, so that's how you encode. You encode totally linear algebraically. Then how do you decode? So decode. So suppose that W is sent and W prime is received. Okay, the point is that we're assuming that basically, like, in order for this code to work, we're assuming that either there's no errors or there's one error. That's as much as we can correct. Right, so if there are no errors, then we can detect this since, let me just say then you just check that P times W equals 0. That was the definition of the Hamming code. Which means that we are getting a vector that's actually in our code, and that's the one that was sent, right? So W is the message that was sent. And so then you just take the first K entries, and that's the original plain text. Okay, but if there's one error, then W prime is equal to W plus some basis vector EI, because there's only one error in it. Right? But then P, if you multiply by this parity check matrix, you'll get PW plus PEI, this is equal to 0, so you just get PEI, which is just the ith column of P. So if you multiply by the parity check matrix and you get a non-zero answer, it means there was an error, and you even know where the error was. The error came from the ith column. So the ith column must have been the bit that was flipped. The ith bit was flipped in transmission. And so this generalized ham encode is really nice because it's even really easy to encode and decode messages. This isn't the, by the way, this isn't the kind of code that's hard to crack. It's not that kind of code, right? It's not cryptography. This is error correcting code, meaning that you can send messages over channels where there might introduce some errors. So to encode a message, it's very easy. You just multiply it by a matrix, essentially. To decode a matrix, it's also very easy. You multiply by the parity check matrix. If you get 0, then you know you got the correct message. And based on the way that it was encoded, you just take the first k bits of that message as the plain text. If you get something that's non-zero, you know that there was an error. And the result that you get also tells you where the error was. Then you just flip that bit, and that was the message that was sent. You take the first k bits, and that's the plain text message that was sent. It's a really cool little linear algebra thing that works because of the linear algebra and the properties of Z2. Okay, so like I said, there's a problem set problem on it, so you will get to know the generalized ham encode a bit more deeply. And now we're going to move on in the next lecture to vector spaces over the complex numbers, because we said that you can do linear algebra over any field. This is a really good example of why you might want to do linear algebra over a different field than R. If you do it over Z2, it has really nice applications to these error correcting codes. We're now going to move on to a different field, namely the complex numbers. All right, see you then.